Okay, here we go. All right. Apologize for the technical difficulty. So, here's what I thought you were looking at. So, extrema, right? Extrema, if you look in the dictionary, it's a noun. Okay. It is the plural. It's meant to be. It represents the plural of extremum. Okay.
Is that important?
That is very important.
Okay.
This is also important. It was an 80s heavy metal band.
Love it.
This is what I was talking about. The 80s, was a fantastic decade, except for musically it left a little bit desired. But we'll forget about the hair metal band. What about extremum? What is an extremum? Well, I'll write it again. So extrema.
It's one of the band members. Yeah.
One of the band members. Extrema is plural of extremum. So let's start with extremum. What is an extremum? Is a minimum or you were right 12 times. It's a minimum or a maximum is an extremum. Okay, so that's what we're going to talk about. That's one of the things that we use differential calculus for, is for finding extrema of functions. And those are important for us. Because functions, remember, don't lose sight of the fact that even though, we spend a lot of time studying math as an abstract thing, which is really important. Because that's what mathematicians do, right? I mean, that's what physicists do. They have to be really, if you're a physicist, then you're a mathematician, right? If you're an engineer, you're a mathematician. You have to understand the abstract body of work that we call mathematics. And then eventually, if you understand this really well, you can use it to model the real world, whether that's economics or sociology or physics. That's where it comes in handy. I think one of the big problems that we have a little bit in the modern approach to teaching math is we try to introduce too many story problems. I think that's really I've got a strong bias against that, and I take this from really smart people who feel the same way, a lot smarter than I am, who Nobel laureates in physics there's kind of a growing movement to just not do so much of that stuff, because really, if you think about this, you can't really do anything until you learn a certain amount of math. There's a reason they don't teach engineering in high school, because you don't know anything. You can't do anything yet. You don't know any math. If you want to be an engineer, you first have to understand the math that actually is going to work to replicate, or to model the real world. And so, you got to kind of think about this a little bit. And I say this for a reason. Math takes you to really cool places, but first you got to learn the math. And so, you might think, like in physics is just inherently, to me, I hope people that are in physics feel the same way, it's just inherently interesting because you get to talk about cool stuff, real world stuff that's interesting. It's just fundamentally interesting because we live in a world that we can describe and predict. But don't fall into the trap of thinking that, like, even if you're in the physics class, that the physics we're doing is the end all be all, because it's not. All it really is doing is it's just preparing you to do much better physics when you know calculus. Because when you know calculus, the physics gets exponentially better than it is right now, right? So this is all, all the stuff we're talking about, and especially the stuff we're about to talk about, is getting you set up to do much bigger and better things when you have more math under your belts, right? When you're later on in life. And I want to spend the day at some point, hopefully before Christmas, maybe we'll have a down day and we can talk about this a little bit. But something I think we really need to, as you guys head off to college, I want to take a little time this year and talk about some of the possible trajectories that math could take you into. And because it's important to know that stuff. I mean, we talk about the beauty of math, but also you're going to have a career. And it turns out that if you want to have a good career, in terms of a lucrative career, a career where you kind of call your own shots, you have lots of free time, great benefits, the majority of those kinds of careers are careers that are going to come out of math and science. That's just the way it is. And I can show you the data on that. Doesn't mean you have to be a mathematician or a scientist, but at least, even if you don't go into one of those pure fields, like maybe you go into law, or you go into sociology, which would not be considered a hard science. Knowing this kind of stuff makes you so much more marketable, and it makes you so much more powerful as an employee or as an academician. I mean, you end up with this stuff could propel you to really big, important things and great jobs in the future. So, don't lose sight of it. All the stuff we do is gonna pay off one way or another, either directly or indirectly, right? So there's my little pep talk for the week. All right, so especially this, and you'll start to see this right away, that this has really important applications in lots of places. Okay, so back to the topic though, Extrema, what are they? We're gonna make a little definition here. So we're gonna talk about this in a couple ways, and I'm gonna be, having said all this stuff, I wanna try to be very mathematical, because we want to be abstract and mathematical, and the applications will pop up later. So how about this? If we say something like, let f be a function defined, and we'll talk about this piece by piece, on an interval I. Okay, and that's just a statement containing C. Okay? What does that mean? Just right there, we got to kind of start. One of the things I want us to begin to work on a little bit is taking this really abstract, almost legalistic mathematical statement and making sure that we can conceptualize this and understand it. That's just kind of like the fine print on a contract. What's this saying? What's this part about defined on some interval I containing C? What's the word defined mean? Say it again. Includes, yeah, I mean, the function just exists there, right? In terms of a graph, we could graph it for that part of the domain, right? The interval, when we talk about an interval, we're talking about input values, right? X values for us most of the time, right? So we're saying there's going to be some set of X values, some interval of X values containing a specific value C. So C is going to be a special point that we'll reference soon. The function has to be defined there, right? We could write an equation or a piecewise function or something that would define this function that we could, if we wanted to, graph. Okay, make sense? Okay, so from there, here are some things then. If that's true, we're going to make a couple statements about that. That f of C is, I'm going to make a little change from the book here with this. This is a better way to do it. The absolute minimum of f on I, that interval, if f of C is less than or equal to f of x for all x in I. What does that mean? So C is a value of x, right, on our interval. F of C is the absolute minimum of f. So what does that mean in just layman's terms?
The lowest one.
Doesn't go any lower. So it's the lowest point on the graph, or the smallest value of the function, the least value of the function, right? I shouldn't say smallest, it's negative. The least value of f on this interval, if this is true. If f of C, so the value of the function at this x value is less than or equal to the value of the function everywhere else on that interval. Does that make sense? Okay, good. So then we can make a similar statement. What am I going to say about an absolute maximum?
If f of C is greater than or equal to f of x.
Yeah, same thing, right? F of x is the absolute maximum of F on I if f of c is greater than or equal to f of x for all x in I, right? Does that make sense? Yeah.
I had a dumb question.
Okay. Well, that's okay. You say you have a dumb question?
But I answered it.
Oh, gotcha, okay. There are no dumb questions. Okay, so then, we could say then that the minimum and the maximum are the absolute extrema, right? This defines absolute extrema on an interval. Absolute extrema happens to also be the name of an album from that hairband. Let's try an example here. What if we do something like,
Were they conscious?
Absolute extreme
What's that?
on an interval.
yeah, want me to go back? So that's what we've kind of defined here. Now we're gonna go look for them. And we're gonna start off, I'm gonna take a graph. Let's take something like this guy, how about?
Was the band aware that they were related to math?
No, there's no way. These guys didn't know any math. So let me go back and look at that picture. You think so? Probably not.
Maybe under all the hair.
And the band may or may not have
So
actually
radical.
existed too. It might just be kind of a Platonian
What?
form for all hair bands, it's possible. Yeah, we'll have to find that out on your own.
It's fine.
So what about this? What if we take the function or Platonic, as you can see. Let's take that function. And let's take it on the interval from, let's go from -1 to +4. And let's look at the graph. We'll just go into Desmos and look at the graph of this.
It wasn't a band.
What's that?
It wasn't.
It wasn't. Maybe not in this universe, but in a multiverse somewhere, they certainly existed and were a huge hit.
Where you get that picture when you just search 80s band?
Yeah, just hair bands.
Oh.
Okay, so there's our picture, right? And we're going to look on the interval from -1 to 4. So let's go ahead and zoom in a little bit. Okay? So we want to know where are the absolute extrema. Let me make a little note here so we can remember what we're doing. If I go. Okay. Where are they? 0, 0? Is that on this interval, is that the largest value? Where's it going to be?
Way up.
Way up, yeah. In fact, I have to zoom out a little bit, don't I? If I want to find the maximum value, I can find out because I could evaluate this function at 4, and I get a value of 16. If we want to see that on the graph, I'll just add that point. So there it is, right? Everybody agree that's the highest?
What does that do?
How'd you just add a point metaphor?
Right there. Desmos is really cool. It does some good stuff.
Is that like
What
a
did you do,
is that a
four
notation?
period?
I just did 4 comma, this is an ordered pair, 4 comma f of 4. Right? In fact, how about if we do this? Hey, we can make this even trickier. Let's make this a, haha, and then we'll just say a equals 4, And then I'll make this f of a. And then I can just slide that around. That's kind of cool, huh? So then that's our maximum value, right? Our maximum value is 16. That's the absolute maximum on that interval. What's the absolute minimum?
-4 or something.
Looks like a -4, doesn't it? In fact, it might even happen at two places, right? We could find the value. It looks like we've got a minimum here at 2, right? So if I make a equal 2, this is supposed to be a right there. Yeah, I got you. Aha. There we go. That's better. Okay, so we get a value of -4 there, or if we let a equal -1, we also get -4. So that would be a shared absolute minimum, right? It occurs at two places, and that's fine. It can do that, right? Okay, let's change the interval. What if the interval went from -2? What's that going to do? Yeah, we could go quite a bit lower, couldn't we? Right, so there's going to be our absolute minimum then. Okay, what if we went from -0.5 up to up to 3? Let's go up to 3. Okay, now let's try this. So if I let a equal -0.5, okay, that's not my minimum. What's my minimum going to be? Absolute minimum. It's going to be -4, and it's going to occur there, isn't it? Right? What's my absolute maximum going to be? If I go, oops, I think I picked the wrong value. I don't want to pick 3. I do want to pick 2.5. I was looking at the wrong thing. So at 2.5, that's not very high, right? Where's the maximum then?
0.
At 0. Okay, so just based on that example, where do you think absolute extrema can happen on a function, on an interval? Say it again.
Anywhere depending on the variable.
Okay, anywhere depending on the endpoints. How would you describe the two results that we got? If I had, when we went all the way from like -2 to +4, where were the extreme values then on that interval? At the endpoints, right? They were at the endpoints, okay? But if I shrink that interval down to that interval, this one right here that we're looking at, where are the extrema? Absolute extrema. In between, and how would you describe where? I mean, there's kind of significant points, right? I mean, if we go to, like, our absolute minimum in this case is at 2. So if I go back to 2, that looks like there's something important going on there. That's not just any point. Why is that? I mean, what about that makes it good? Say it again. A vertex. Kind of, it's like a vertex, isn't it? I can see what you're getting at, because it's the bottom of the valley, isn't it? Right? If you think about this as a two-dimensional topology that our ant walks on, if he's going for a hike, that's when he's in the bottom of a valley, right? Where is the absolute maximum? It's on the top of a peak, right? So we can get, if you think about this, we can get absolute extrema either at endpoints, right, the end of his Earth, that might be the highest point, right? Or it could be at the top of a two-dimensional mountain, top two-dimensional peak we'll call it, or the bottom of a two-dimensional valley, right? The endpoints are easy to find. Those just are the edges of the interval. But the next issue is, how could we find these places in general, maybe without a graph? Or what if the graph is not as well behaved as this one, where the peaks and the valleys occur on integer values of x? How would we have found it then, right? That's a tougher of the two questions to answer. The endpoints are simple. The endpoints are just defined by the interval. The x value for that endpoint is -0.5, and the right endpoint is at 2.5, because that's how the interval's defined. Those are obvious, right? But finding x equals +2 or x equals 0 could be harder in a different situation, right? That's what we got to focus on. Well, and that's what it's going to be. So let me just superimpose a picture on top of this. Right, so I want to take a picture of this for your notes. Okay, so what can we say about this? Well, we have names for these. This point right here.
Didn't you choose the?
Oh, I did, right. So this one, so now in this our interval here is from, what did we say, negative 0.5 to 2.5. So then we'd be cutting it off like right there and right there. So everything in the orange box is now, that's the world of that. Yeah, that's its derivatives. That's it. So this is what we call right here, a peak like this. Is a relative maximum. Sometimes we'll call that, or it could also be called a local maximum. Depending on the textbook, those are two words you would typically hear. Okay, this down here is what we would call, so this is a valley, right? Is a relative or local, whatever you want to call it, minimum. Okay? Why is that? Why would we call it local or relative?
It's a certain.
It's only in the envelope, so.
Okay, it's only like locally, right? Relative to that point, the points immediately around it are going to be lower, right? Relative to this point, the area around it is going to be, the points around it will have greater y values. It doesn't mean everywhere. If we extend our interval out this way a little bit more, we saw that the ant, if he walks to the left, he's walking down this slope that takes him to places that are lower than this, right? But it's still a relative minimum, because if he walks one step to the left or one step to the right, he's going to be going up above that point, right? Does that make sense? So that's the question.
If it was -2, would that still be a local minimum? Because something one to the left and one to the right?
Oh, okay, I see. So you mean if the edge of the interval was right here?
Well, no, if the other edge
Mm-hmm.
was farther to the left.
Yeah, okay, yeah, so if the other edge, let's say on this interval right here, on that interval, or make that a -2, okay? It still would be. It's still gonna be a relative minimum, because a relative minimum doesn't depend on the endpoints. It depends on the shape of the graph, right? If it's a point where, if it's a valley, if the graph looks like a valley, it's a relative minimum. If the graph looks like a peak, it's a relative maximum, regardless, okay? So then we could say, if we want to go back to our question of, where are the absolute extrema, well, then they would either occur at endpoints or at local or relative, whatever you want to call it. It's called, we'll call it relative. At relative extrema, either relative minima or maxima, right? Those are just plurals, right? You get the idea? So we'd have to check the values at all of those places. So like if we were going to do a problem like this, for example, let's say, let's pull one out of the back here. Well, how about this guy? If we wanted to, it says find the absolute extrema of f of x equals 3x to the 4th this interval from -1 to 2. And by the way, like in our book, they don't even include the word absolute there. And this is kind of something, I know this is, I wish there was just like one standard that every book would follow, but there's not. But do you understand that if we talk about find the extrema on an interval, the context there would imply you're talking about absolute extrema, right? You want the highest and lowest values. To be precise, you should say absolute extrema. So where could those occur? The absolute extrema.
Endpoints.
Endpoints or internal relative extrema, right? AKA peaks and valleys, right? Okay? So we gotta know how to find those. How are we gonna find those? If we go back to this picture, how would we find that place right there using calculus? What's unique about that place and that place? They have slopes of 0. Aha. Slopes we get from the derivative, right? So what would be a process that we could follow to try to find the x values where we're going to have relative extrema?
Take the derivative of the function and set it to 0.
Yeah, take the derivative of the function, set it to 0, and find the zeros. Solve that equation. And the x values that make that happen, meaning the zeros of the first derivative, those are going to be candidates for relative extrema. Okay? Does that make sense? Okay, but there are some limitations to that. I'm going to show, I could trick you with that. I can draw a function that has internal zeros zeros of the first derivative, so places where the first derivative is 0, that don't end up being relative extrema. That's possible. I'll show you. Here's an example. So let's say we're going to go from A up to Z, our interval. And this is going to be our function. So our function looks like it's going to go okay, where are the places on that function where the tangent line is horizontal, which means 0 slope? Derivative is equal to 0.
At the very top of the peak.
Okay, so right there's one. Where else?
Right next to.
Yeah, I didn't draw that very well, but you get the idea. That's supposed to be a place where it has a 0 slope, but it's not a peak or a valley, right? This is, by the way, what we call, and this won't make sense to you now, but it will shortly. This is what we call an inflection point. That'll make a lot of sense in the future. I can't really define it right now because there's some stuff we don't know yet. But it's a false alarm, right? It's a place where we would have found the value of the derivative to be 0 between A and B, but it would not have worked out to actually be a peak or a valley, right? So then what we could say from that, if we want to come up with a rule, a test for finding those, we could find all the places in our interval where the derivative equals 0, and then we'd have to check them all to see if they're actual peaks and valleys or false alarms, right? Does that make sense? So what would we call those places? Well, we could say then we could call the x values, so here and here, we'll call this C1 and this C2. We could call those critical numbers, right? And that's what we call them. Those are places where those are the values of x where we might have a peak or a valley based on the derivative, but then we have to check them to see if they actually pan out, right? So where do critical numbers occur? We're going to make a list. Critical numbers. Critical numbers, they could be places where f prime of c equals 0. That would make c a critical number, right? Right? Okay, what else though? I'm going to draw another example of a graph, and I want you to tell me what we forgot to include. Okay, so how about this? What if we do, there's a, keep doing this, you're going to make B out there for a minute. So where are the critical numbers for this guy? Top. Okay. So that has to be a critical number because that's a place where we had a peak, right? That looks like one right there too, doesn't it? Right? But what about that point? That's a valley, isn't it? Would you agree that that's a relative minimum? It fits the description, doesn't it? Because if the ant moves to the left or the right, he's going to take a step up, right? That is a valley. So what about this one? How are we going to find out? That's not a place where the derivative equals 0.
It's
Where what?
it's
It's undefined.
It's undefined. How come? Why is the derivative undefined there? Sharp corner. Yeah, it's a sharp corner, right? So we're going to find other, we could categorize these. This is kind of cool. We're going to find nice smooth peaks or smooth valleys. Those are going to correspond to critical numbers where the derivative is equal to 0. But we're going to get these jagged peaks and valleys at places where the derivative is undefined, right? So we got two kinds of places where we need to be able to look for our critical numbers. We're going to look for places where the derivative is 0 or places where the derivative is undefined. And that also makes C a critical number, right? Does that make sense? Okay, so let's try a problem like this then. We're going to go find all the absolute extrema. We're going to find the endpoints, and then we're going to have to go locate the internal critical numbers, and then we'll just check them and see if they work. Okay? Question so far, though. Does that make sense?
You go back to the.
Yeah. I'll publish these today, too, so they'll be up there, all the notes. Okay, let's go back and do our previous example. I think I wrote that one. Let's go back to that one.
We have a minute left.
Was that all we have?
Yeah.
Oh, why did it stop? Just gotta keep going with this.
Yeah, oh no, now it's this whole weekend to forget all of this.
Yeah.